So this is a petrochemical and refinery master electrical plans and what a good system looks like. I'm Vince Wedelich, and I'm your IEEE Power Energy Society Houston Chair. And I work for Burns & McDonnell. We're an electrical engineering company consulting. This is something that I've always, I think the first time I did this, I can't remember, but I've always wanted to pull up to a company and see, that our company should have a zero policy, zero safety incidents, zero power failures with the fastest power recovery, zero flares and process leaks, and zero process downtime. This is what, I envisioned. I think it was like 2004, and I tried to push this agenda. Maybe it wasn't that long ago, but whatever it was, I put that out there, and I'm slowly starting to see this. I pull up to a facility, and I'm starting to see these zero policies, right? And it makes you feel good because, most people don't realize how bad it was in Pasadena, right? How bad it smelled, right? We used to call it Stinkadena. And the reason, it wasn't anything wrong with Pasadena or the facilities. They were following the guidelines by EPA or just however they do it. But they had leaks, a lot of leaks. And these leaks were coming from valve stems. They were coming from areas where, there's little leaks, right? It could be where they bolt two flanges together. And so it just smelt, right? You just always smelt these places. Now what they do is they've come through and they've added these little tags, these tags where they go in there and they do leak detection. And it's phenomenal how much it's improved, how nice it is out there, because really, you're just breathing that stuff all the time. And so years and years ago, we just didn't have these rules in place. Now they're required to go out there and to check for leaks, to check for these things, which is ultimately going to make it a safer place, going to make it a more profitable place, and they'll have less downtime. Let's see here. There we go. So, obviously, it'd be great if everybody could get on board and save the bottom line. As far as petrochemical facility owners and refiners are advised to set a goal of zero power failure and fastest power recovery and share the goal with all the employees, including people outside the plant. Put this goal out there and then everybody do your best to hit it, right? I mean, that's the key. When a refinery petrochemical facility shuts down, business profit is gone, right? Maybe you didn't know this, but if one of these typical refineries goes down, they'll lose $1 million in 1 hour of revenue. That's a lot of money, right? Not to mention that it takes time for them to come back up and get that system up and running. A refinery is like a balancing thing. Everything has to be just perfectly balanced. Any interruption into that balance can cause it to all come down, right? So it's a very delicate balance sometimes. When a refinery, we talked about this, but for the CEO and the maintenance worker, everybody needs to be involved there. Any employees that are offered a key contribution in terms of ideas and innovations to increase reliability, availability of a power system should be offered financial incentives to avoid power failures and to avoid process interruptions. The Power of Habit, that's a good book. You can take a look at it. That'll help drive it home. Some of the reference data, right? Long-term optimization, refinery power failures, causes, costs, and solutions. Integrated advanced relays on medium voltage switchgear safety systems. That was actually a paper that we co-authored with P66, and it was presented in the IEEE PCIC on 2013. You have your OSHA 1910 119 process safety management of highly hazardous chemicals. Arc flash mitigation was another paper, but if you follow arc flash mitigation, you can save lives and you can reduce, equipment failures and equipment being just totally destroyed, for that matter. Many papers published and issued by IEEE. So an abstract here, the material used for this presentation was readily available from the internet, IEEE presentations. The presentation is for educational safety and process improvement purposes only. You can review what an electrical master system or plan study is. What you should do when you're doing an electrical system master plan is you should identify the system improvements related to reliability. You should, look in the history, right? safety and maintainability for projected load expansion at the refinery petrochemical facility for the next 5 to 20 years. The master plan and the ideas presented were geared toward creating a good foundation for the future of an electrical system, primarily through upgrade and replacement projects, and then illustrate what a good system looks like. So my point is you know, as electrical engineers, as electrical infrastructural project managers, these jobs just aren't going to happen unless you tie them to the process, right? The process is what they make money with. That's where they get their return on investment. If your project is a project you really want to do because you know that's an unsafe piece of equipment, that's one thing. But if it's just a nice to have, you need to make sure that that nice to have is built into your philosophy, into your design guidelines, and then that you tie that into the larger process projects, and it'll get funded. Again, I'm your IEEE Houston past chair, but also the PES current chair. I'm an associate level project manager and electrical engineer at the Houston T&D Power. I think we call ourselves IES now. So the OSHA reports. What are the 100 largest losses from 1972 to 2011? Large property damage, losses in the hydrocarbon industry. I think everybody can kind of think of a few of them, right? So what refineries, petrochemical gas processes, or terminal and distribution systems all have in common? Well, depending on their location, they could all have earthquakes in common. They could have fires, explosions, hurricanes, flooding, vapor cloud explosions, corrosion, pipe racks. Pipe racks can fail. Especially some of these refineries are upwards of 60 years old now, 50 to 60 years old. Mechanical damage, and these mechanical damage or these overloaded pipe racks might not even be addressed, and they should be addressed. Things should be looked at. So here you can see a large explosion, a big fire, right? So here we have an example where we have 5 people were killed and 2 seriously injured following an explosion at a plastics plant producing 200 million barrels per year of specialty grade PVC. The highway was shut down and local residents evacuated. The explosion occurred in a reactor where vinyl chloride and vinyl acetate were being mixed. Up to 75% of the plant was destroyed in the explosion. The explosion was felt 4 miles away. How can you mitigate that, right? You know, you can implement the SIS systems, the safety integrated systems, and that's really what it's all about, right? Going after these systems, analyzing your processes, doing process hazardous analysis, and trying to determine what is going on and seeing if you can address it before it becomes an issue. Here's another example. A release of hexane created a vapor cloud which ignited an electrical motor, causing an explosion. This resulted in damage to the unit and to 20 injuries. The plant was eventually replaced. So here they just completely shut the plant down because of this hexane created vapor cloud. Again, you can implement your safety instrument systems and address the area classification issues. Area classification issues are a little bit more complicated than most electrical engineers think. And for some reason, as an electrical engineer, we are required to perform these electrical area classification studies. And a lot of people don't realize the benefits and the time that it takes to go through and analyze these systems. I just finished a large refinery. Took probably upwards of, about a year and a half to do it, and we still have a few more units in the MOC, the MOC process. But at the end of the day, and we've done this for more than just one refinery. We've done this for other facilities as well, and it's been a big issue and a positive responses from these clients. What we do is we go through, we identify the different hazards, we look at how things are. We've even implemented something where we turn an engineering layer off or turning an engineering layer off or on or off, and that every piece of equipment has a bubble around it, right? And when you turn off the engineering layer, you're looking at the outer bands. But as you go through this in the labs and whatnot, you can find the issues that could potentially cause a failure, and you can help them fix them. So here's an accident occurred of a Melu cellulose manufacturing facility located at site at 4:26 in the evening. An explosion occurred and was followed by a fire which was extinguished at 11 that night, the same day. 17 people who were working at the site were injured in this accident, 3 critically, 5 seriously, and 9 were minor injuries. There there was one minor injury off-site. Static electricity was the cause of the problem, right? Most people don't realize that, but if you have large tank farms or if you have these large areas and you have not dealt with your static electricity issues and mitigated this, you can create a major, major explosion, right? And so in this case, there was a powder dust explosion, right? So when we do class 1, div 2, or electrical area classification studies, we have class 1 is for gases or vapors. We have class 2 is for dusts, right? And so this is a powder dust explosion, right? So, and there's certain rules that follow and certain ways to mitigate these issues. We have a lot of new plastic plants in the area, and we need to make sure that, that they comply, that they're designed properly, and that they won't have dust buildup and ultimately an explosion. Hurricane and flooding, oh my God, we get it all the time here, right? I live in Meyerland. The front of my house turns into a river, right? It's ridiculous. If you leave your car out there, it's gone. Storm surges, flooding, and high winds caused significant damage at the site. Force majeure was declared, and the most heavily damaged portion of the plant remained offline for 152 days. Millions, billions of dollars were lost during this hurricane. The solution, these are coastal sites. The flood maps need to be updated, and electrical equipment needs to be raised into elevated power control rooms, have an alternate power source. So if you're, a lot of these places aren't going to move. They're going to stay there. But if there's ways where you can mitigate these issues, you can lift these powerhouses up, you can lift up critical processes, and you can, or you can even create flood barriers, right? And actually flood walls and quarantine off these areas, which isn't a bad idea, actually. Here we have a massive explosion, occurring using ammonia nitrate. And I think we just saw this happen in Beirut. They had the ammonia nitrate ship that had a bunch of ammonia nitrate in it, and it's highly explosive. They use it for fertilizers and things of that nature because of its nitrogen content. So this warehouse contained approximately 300 tons of off-specific ammonia nitrate crystals. The explosion had a strength of a 3.2 magnitude Richter scale. That is a big explosion, right? Left most of the plant in ruins and caused damage to surrounding areas. 30 people were killed in the blast, and approximately 3,000 people were injured. And this is simply an area classification issue. Most people don't realize it, but sugar plants, ammonia, fertilizer plants, obviously petrochemical facilities and refineries all have hazardous material that will explode if it's released. It will release from time to time. So you need to make sure that if you're designing your facilities, or if you're unsure of, does my facility meet certain area classification standards, then you can ask, right? And we can help you out. We can go out there and look at these places. Recently, I've had facilities where their insurance has gone up because the insurance company says, you know what? A car or a vehicle or a truck or whatever can drive through these facilities, and there's really no way of them knowing what they're driving into. 100% accurate, right? So after you finish your refinery, your area classification study, you can go to an API 2216, I think it is, and you can look at these different areas where you could actually have a truck or a vehicle or a small maintenance vehicle create a hazard or an explosion, and you can barrier off for these areas with signage and whatnot, right? So here, an explosion and a fire occurred in an olefins unit in a petrochemical facility. The incident originated in a cracked gas compressor in the olefins unit and was caused by a failed air assist check valve on the 5-inch diameter, 500 psi discharge line from the compressor. Upon closure of the check valve, one of the pins holding the 2-piece check valve stem broke and allowed it to open in the opposite direction. This led to a gas leak, ignition, explosion, and ensuing fire at the partially enclosed compressor building. The explosion damaged a line to the quench tower which fed the fire. The fire was allowed to burn itself out. Can you imagine? And we saw that too at different facilities where they couldn't get safety people in there, and they just allowed the facility just to burn. About 30 workers were treated for minor injuries. Thank God nobody died, right? So again, this is you can address these with safety integrity systems, SIS systems, process hazard analysis, and area classification issues. You could have double block and bleed valves and things of that nature. You could have car seals put in, et cetera, right? So fire and explosion, a vent connection failed on a compressor suction line, releasing gas, which led to a violent explosion and widespread damage. This was believed to be fatigue due to vibration. A lot of people don't realize this, but a lot of things vibrate, and you need to understand if you've got a lot of vibration, the stresses caused to the steel, to the pipes, and everything around that device might not be ready for it. That's more of a dynamic failure versus a static failure, right? So the electrical network, almost all parts are vibrating at 100 hertz, resulting in metal fatigue. So when we have motors and we have different components, transformers, whatever, they're all vibrating at 100 hertz. You know, I said this earlier that most of our infrastructure, most of our refineries, chemical facilities are old. Upwards of, you know, it used to be 40 years old, now they're 60 years old. So, you know, the oldest assets are about 60 years old, maybe even older now. The average asset base is about 30 years. However, assets do not have a perpetual life as normal wear and tear takes its toll. In the energy distribution systems, the assets are relatively old. Distribution companies expect a large number of assets to fail because they reach their end of the life from 1 to 21 years. From now, current, and at this time when I put this together, it was 2015, right? So now we're at 2020. So now you got less time, right? Age infrastructure, vibration and corrosion influences build up over time. Nobody knows for certain how fast deterioration will take place. The best estimate for a lifespan is between 40 and 80 years, depending on the type of asset. And what you do is there's actually the IEEE Gold Book on reliability. I know it's controversial sometimes, but that's a good starting point, right? And as you go through these facilities and you check to see what they're rated, check to see when they were manufactured, check to see if there's repair parts even available, you can come up with a number or a lifespan or a remaining lifespan for that piece of equipment. If you're at that lifespan or if it's just dangerous, you need to think about putting that on your, your budget and getting that replaced. This, this means we can expect at least part of the asset base to reach end of life within 1 to 11 years. And that was based on 2015. So end of life is defined as a non-repairable failure of the asset. The failing assets will have to be replaced, which could potentially double the total workload in this 20-year period. Unfortunately, we have aging personnel, right? So to parallel to aging equipment, engineering staff retires after 40 years in service. As most of them were employed during the 70s, we see a lot of this. A lot of them are starting to go away, if they haven't already gone away. We can expect a large part of them to retire in the year 2016, and we saw this. And I'm sure that 2020 COVID-19 hadn't helped this at all, because if somebody was on the verge of wanting to retire but decided, why should I retire now? I like going to work. Now they've been home for a good 9 months, and they're probably going to just retire. So about half the workforce will retire by the year 2013, it says. So here we have, a spiral of decline, right? We have the workload, we have available personnel, we have maintenance and requirements and replacement, and we have failures. So what we really need to do is we need to train a lot of people real quick, right? 1 in 5 young people will need to become an engineer if we have any chance of addressing severe skills shortages and rebalancing the economy toward advancing manufacturing. New research has warned. There is no getting away from the fact that women and minorities are substantially underrepresented in manufacturing at this time, when industry needs to be tapped into every potential talent pool to assess the skills it needs. There might not be enough people to fill these bills or to fill these roles, so technology needs to step up and to provide opportunities for 1 or 2 people to do what 10 people used to be able to do. And I think that's the key there, right? Demand is high, it's getting higher for qualified engineers. With a number of baby boomers retiring in 2017 and in 2022, the big fear is that there's not enough individuals coming into the workforce to replace everybody, especially in the engineering fields. The dilemma of a shortage of skilled engineers has become a prime topic of discussion across the country. The present-day labor market for most United States-born engineering graduate remains relatively competitive in a time of high unemployment after large manufacturers and firms have consolidated operations during the recession. Many engineers have also have to compete with highly qualified candidates in China and India. Now I guess you'll start seeing that in Mexico and Vietnam and areas like that. I'm not opposed to having somebody in India work on a project. I think it helps the industry. I think that if you can get more people to offer advice, offer solutions, it's a better thing. But recruits indicate that demand for engineers and more technically inclined workforce in the U.S. is only expected to grow, right? So here we have, petrochemical refinery shutdowns from 2009 to 2012. What was the major causes, right? So here you have the major cause right here is a mechanical failure, right? 46%, that's a big pie, chunk of the pie. Maintenance is 23%. Electrical is 19%, and other is 12%. So this was 1,700 refinery shutdowns, or roughly 1.2 shutdowns per day, right? Causes of disruption. So here you have surges, weather, breakdowns, fire, unspecified. I don't know, unspecified. Unfortunately, 60% of the causes of electrical disruption are not specified. Most of the unspecified power failures were listed as power failure occurring at the refinery and causing flaring or similar statements. There's still a lot of refineries, a lot of facilities out there that have electromechanical relays, and they don't have the proper automation that they need to properly analyze a failure. And these relays from different vendors like Eaton, for example, or for Schweitzer or ABB or any of these electrical equipment manufacturers such as Square D or Schneider, they all have smart electronic relays, and they all have smart systems that can be put into place for relatively cheap and will allow you don't even have to have an intelligent staff on hand to analyze this data. They'll actually analyze it for you, and they'll tell you what happened, right? So, flooding during hurricanes. Although the wind and debris are most commonly cited causes of hurricane damage for Gulf Coast refineries in the U.S., where hurricanes hit most often and hardest, the greatest hurricane damage is the result of flooding. And we saw this the last time. The water levels were super high. I mean, like 3-4 foot in different facilities around here. Structural integrity. It is important to understand there's a difference between reliability supporting piping and process equipment versus being able to stand in place with piping and process equipment. In many existing facilities, previous expansions, modifications, the age of structures, as well as unknown conditions such as materials, have drastically reduced the overall reliability of the support structures. And you see this in the pipe racks, and that's the big issue, because over time, you can see the first original pipe rack, and then somebody built on top of it, and then somebody built on top of that, and then somebody built on top of that. And so it's just it's a compounding issue, right? So I don't believe that the original engineers ever thought that it would be that heavily weighted, right? In many instances, the in-place condition of many support structures are already well below current minimum standards of reliability, not to mention good practice standards. So here we have a new steel is added to an aging pipe rack. This can occur 3 or 4 times. The engineers designing the pipe racks could not have anticipated this, right? And we have like PIP standards that allow you to look at the pipe rack and say, hey, if it's 5% or less or of the existing weight that's in there, then it's not a problem. Well, I do that today. Then somebody else follows me 3 years from now, and then somebody else follows me 3 years from now. When does it become too much, right, for that deal? Another issue is here we have a wrong location of a small bore piping connection, right? So you have this little bleed valve at the bottom, this little small gap right here, and then you have this piece of iron right here. And what happens I don't care if it's a electrical conduit or if it's a cable tray or if it's a pipe, as it gets hot and cold, it expands for the hot pipe, it contracts for the cold pipe. And if that gap right there isn't large enough, right, what'll happen is it'll expand and contract right into the metal, right? And what happens is it'll knock it off, and then you're dumping whatever product's in that pipe on the ground, right? Here's another example of a pipe. You know, as an electrical engineer, you don't usually see this, but you know, once I explain it, you'll probably look up into your racks and see it. So here you have a stop guide of a stop instead of a guide, right? So here we have a stop, and another stop, and another stop. And what it's supposed to be is you're supposed to have a guide where it looks like a pipe shoe, right? And the pipe is bolted to this or welded to this shoe, and it allows it to slide this way or this way, right, during contraction and expansion. And if it's not installed properly, it can actually pull on these bents, right? It can actually cause these columns to bend, right? So, and that's exactly what happened. We have an LPG fire because of that. The key issues: lack of freeze protection of dead heads, or dead legs rather. Failure likely resulted from water trapped in a propane mix control station. Dead leg freezing due to low ambient temperatures. Lack of emergency isolation of equipment. Lack of fireproofing of support steel. What they do is they'll take a steel column and they'll surround it with concrete, right? And that becomes a fireproofing. They also have different new materials that they can use as well. I prefer the concrete or anything like that. A lack of fire protection for high pressure LPG services. And then on top of it, they had a chlorine release, change to sodium hypochlorite systems. If you change to a sodium hypochlorite system, then you're taking the salt water, or you can even truck in sodium hypochlorite. You don't have to have the chlorine there. Although chlorine certainly is probably a cheaper way to go, right? And that's probably why they use it. So these are all these issues you can address by having process hazard analysis studies, right? So here we had multiple unit shutdowns. Since most refinery petrochemical facility units are integrated and sometimes share the same power supply, power failures could lead to a shutdown of these integrated units and the production loss of many refined products, thereby magnifying the potential loss. So a facility in Alaska experienced a power outage. The hydrocracker and another unit were shut down. In Texas, plant experienced an external power failure that knocked its plant and other refineries in the area. You see this time and time again. A refinery, they'll have two transformers on one substation. One of the transformers goes bad for some reason. The protection's not, doesn't isolate it quick enough, or there is no means for it to isolate. That one failure translates into 4 or 5 different facilities around it failing. So here we have safety and reliability approval. Most companies care about 3 values: finance, reliability, and safety. So when you're trying to get these jobs approved, or if you're trying to make your plant safe, you need to make sure that you understand the financials, the reliability, and the safety. The manageable optimization process a single objective is pursued. The common way forward is to express safety and reliability in monetary values. What is the cost of the bottom line if it is not corrected? What would happen? Obviously, if somebody dies, that's just catastrophic, right? Even if somebody just gets hurt, it's not. You just don't want that on your head. And to think about it, there's no acceptable monetary value that can be placed on safety and saving lives, right? Production loss and profit penalties. When a power failure occurs, a petrochemical facility unit or units, an entire facility must be shut down and production is lost. And like I said, you can lose, easily one of these large refineries in Baytown's $1 million in 1 hour, right? So these are large facilities. Even the small average sized ones is 80,000 barrels per day will lose $68,000 per hour. Obviously that's dependent upon the cost of crude and their crack spread. Here we have a case study. Facility was shut down in 28 October to 20 November. Due to that Superstorm Sandy, if you recall. So that was a massive flood after that superstorm. According to the company, the expenses related to the storm were $56 million before taxes. The loss did not include missed production for over 3 weeks. Based on the refinery's nameplate gasoline production capacity of 145,000 barrels per day and distillant production capacity of 115,000 barrels per day, a utilization rate of 85%, and an average spot market price at the time of $2.80 per gallon and $3 a gallon per distillant, The New York Harbor during the shutdown period estimated revenue loss was over $650 million bucks. So there's big dollars here, you know. So if you're not thinking about these, and most people don't, they don't think, wow, you know, we've been here forever. Why would we have a big flood? But it's getting worse, right? Winds are getting higher. A lot of the things that they're pushing out there to support different electrical products just cannot support them. I see this time and time again, and I'm not going to name names, but you know, there's prefabricated steel pieces that people put up on top of these pipe racks that are not capable of supporting this high wind conditions, right? So you can have possible legal liabilities here. So aside from your missed production, outages prompt unnecessary flaring, hydrocarbons to avoid unsafe conditions. Whenever you flare, you get fined by EPA, right? So it just compounds the issue. You can also have, you know, different organic compounds, you know, polluting the area as well, right? So potential legal liabilities, right? A facility in Texas paid over $87 million in fines issued by OSHA, along with undisclosed amounts of civil suits related to an explosion and subsequent fire in Texas City and Texas refinery petrochemical facility that resulted in 15 workers' death and over 170 injuries. It's a big deal. So what can we do as electrical engineers? You know, we can you know, teach people about the electrical supply, right? Electricity is the lifeblood of the refinery petrochemical facility operation. There's so many different situations where they're going away from steam and they're going to more electric devices, right? Optimal design, excellent construction mean nothing if the plant cannot receive a constant and reliable power supply. Nobody even thinks about it. Everybody's like, why do we have to do that? This thing works all the time. It works until the lights go out. Then they realize, hey, we really need to do something about this, right? So what you want to do is you want to manage your electrical outage, you know, refinery outage mitigation. You want to do your risk management, you want to do prevention and protection. You also want to do crisis management, recovery, and restart. In handling a risk management, you want to take a look at, you know, the most reliable equipment available on the market that can withstand disruptions during weather, power surges, blackouts, and other outside elements. Since no equipment is perfect, reliability engineers and operators need to prepare for worst case scenarios as well as most frequently occurring possibilities, right? You don't want to go overkill though. You don't want to, you know, build something that's a Taj Mahal. That doesn't need to be that way. Especially if you're, you know, upstream. If you're upstream and you're in these wellheads, some of these wellheads don't last that long. They might produce gas for 10 years. They might only produce oil for a year or two. So you don't want to put in a piece of equipment that's going to last 40. Maybe a better idea would be a mobile platform, right, where you can build a nice piece of equipment that can be used at each site or at each wellhead as it's needed. Crisis management, when a problem does arise, the second part of the strategy, crisis management comes into play. This involves the recovery technologies that allow for safe shutdown and continued operation and the restart methods that will not lead to the same problem that caused the previous failure. And I've seen this before where they have, you know, if a power failure occurs, this refinery can actually lose, it can actually cause death because it starts to release product. That's something that needed to be mitigated pretty quick, right? One of the most preventive measures of a hydrochemical facilities can take place to have an efficient maintenance program. You want to make sure that you do have a good, efficient maintenance program and you have tools necessary or in place to monitor your equipment. But you also got to be cognizant that sometimes when a maintenance guy gets out there, he might cause more trouble than it was just to leave it alone. So you want to balance that as well, right? So there's 3 times higher for components that are not part of a scheduled maintenance failure, so they'll fail. So certainly if you don't maintain your facility at all, you're suspect. You know, you probably have some issues. And there's different programs like the reliability and TPM improvement projects or programs where you can go through this and you can set up different programs to help you maintain your equipment, right? So here's a reliability system. You know, you certainly want to have, you know, everybody in the room is smart and can without a doubt show reliability is not a bad actor as it looks using the Monte Carlo tool. I've seen this over and over and over. Somebody can overanalyze something and they can say this is not a problem, right? The likelihood of this happening is not going to happen. But when it does happen, they say, wow, well, that was an outlier, right? You know? So if you have a radial feed system, and what I mean by radial feed system is you got one source, right? Comes off the pole into a power panel, and then that's what feeds the refinery. That is your single point of failure. And if you want to make sure that you balance that situation to make sure that if that single point of failure happens, what is the refinery going to do? What is the shutdown sequence? Are there any backup systems like UPSs, generators, things of that nature, right? So this is certainly the cheapest, most cost-effective solution, and there are a lot of facilities out there with it, but there's no redundancy here, no system reliability. A better system would be a dual feed system. And here you'd have two sources of power into like a main tie main. And what would happen is you'd have an ATS scheme, an automatic transfer switch scheme, where if one power source went down, it would automatically close the tie and allow the other system to supply it. Or you have truly A-B systems where you have an A bus and a B bus, and you're feeding all your A stuff with the A bus and the B stuff with the B bus, and if you lose one or the other, you're still okay, right? So you want to make sure you kind of think it out. So here's a single tie arrangement where you have a main tie main, and this would be like A bus and this would be like B bus. Here's a double tie arrangement, and the reason why you would have a main tie main is a lot of people want to look at that point right there and service that point. If you only have one, you can see that you could never take down this tie. You could never go in there and torque it, you know, on both sides of it. So that's why they have this arrangement here. I've also seen them where they'll put a main tie and then another little circuit right here for a generator, so they can put a generator right in the middle. Not a bad system. So there's all kinds of advantages to dual power systems. There's advantages to loop feed or ring bus systems, and there's advantages to a combination of radial, dual feeded, or looped systems. You know, you want to make sure you formulate your strategies to mitigate power losses. That's the big deal, right? You want to find out exactly how much would it cost, what would be the loss if I lost power today, right? If I'm in an office, well, I could have loss of production. These guys would be sitting here twiddling their thumbs. Can I mitigate that with a simple UPS circuit and just put certain circuits on UPS power? And that way, work can continue. A lot of times just using these laptops and their batteries is a bit of a lifesaver there. You know, you can keep things going. You can have impacts on refinery and petrochemical facilities for power failures. So here's the impacts of power failures. You know, you got your power factor impacts right here. You can have asset management, you can have energy efficiency, financial performance, plant safety and reliability, negative publicity, environmental concerns and reliability. So you want to make sure you kind of balance these between the negative publicity and the reliability, right? And your financial performance. Power independence, on-site power generation via combined heat and power, CHP units, and microgrids might be worth considering, especially now with these new battery systems. You can come up with a fairly sophisticated system for fairly inexpensive. And usually it'll pay for itself, especially if you're allowing, like I just saw, can't remember the, Generac. Generac has a new system out where they have a battery and then they have the utility system and then they have solar panels. And what they've done is they've just kind of taken the solar and they charge this battery, which is like a wall battery, similar to the Tesla batteries. And then what they do is they look at the peak times when power is the most expensive, and they'll provide power during those times. So it's not a bad system. These systems are getting better and better and better, right? But you have to get everybody online, you know, to save the bottom line, right? Everybody has to join into the systems. When you're looking at major equipment and electrical systems, you want to look at the generators, the motors, the power and control cables, the transformers, UPS systems, which is uninterrupted power supply systems. You want to look at your battery chargers, your battery banks. You want to look at your switch gear and control gear and your panels and your lighting, right? Typically, an oil-filled power transformer will last for 50 years, and then it needs to be replaced. 5 to 15 kV medium voltage switchgear is usually good for about 40 years. A medium voltage MCC is usually good for about 35 years. 40 volt MCCs are usually good for about 30 years, and also solid dielectric medium voltage cable is good for 30 years. I didn't say it in here, but there is the PILC, paper impregnated lead cable. That cable lasts and lasts and lasts, and Okanite still produced some of it for a facility up north. It is probably a cable that'll last for over 100 years, right? So transformers, almost every malfunction is a result of a failure of a device's insulation system in a transformer. So what'll happen is, if you have an overheating condition or if you have a fault, it'll actually cause insulation failure, right? And so that's what you're looking for. And there's certain tests that you can implement and certain, companies that'll facilitate these tests to look at the oil, to look at all these different insulation factors, right? So this is what a large transformer looks like in a refinery. And this is a big, big piece of equipment right here. I usually take young engineers out in these refineries and I say, what's that, right? They have no idea what it is, right? They're looking at it and they're like, I don't know, it's a box of some sort, right? They just don't know. They don't learn this in school. They've got the calculations down. They know how to solve a problem. They know how to solve these math problems, but they physically don't have the experience to even see what they're trying to install. And this becomes more of a physical problem than anything else, right? And then you've got your different cables. You want to understand all your cables. You want to understand the different types of systems that are installed. Here you have a fairly robust armored cable, right? So you've got your different cables, 300 volt, 600 volt, 5,000 volt, 1,500 volt, 15,000 volt. You want to understand your switch gear and how it's installed in your system, or even if you have switch gear, you might not even have it. You want to understand if you have arcing issues, right? If you have an arcing issue and you have an electrician going in there opening a breaker, that arc, if it explodes and it hadn't been fully tested and it creates an arc, could kill him, right? He has to literally wear like a bomb suit to go in there, right? So an arcing event can cost a refinery or petrochemical facility as much as $15 million per incident. We've done a great job of mitigating this, and I think a lot of people, a lot of the relay manufacturers, a lot of the ETAP, the SKM, the Easy Power, these guys have done a great job of providing the tools that we need to mitigate arc flash issues, right? Motor control centers, a lot of people rely on these. They work real well. They're easy to pop out, easy to pop in. You can pull a bucket out pretty quick, and you want to make sure that everything works the way it's supposed to, right? And you also, if you are working with these things and you're locking something out, you want to make sure that something else can't start it, right? So here's a complete, well, almost a complete system. So here you have a utility system from an outdoor source, right? Comes in here and feeds a switchboard. So a switchboard has a busway that goes to a panel board. Could be a conduit, could be anything. From the panel board, you go to a transformer. From the transformer, step down to 120 volts, where you see receptacles and lights and whatnot, right? So here, this same switchboard goes over here and feeds a motor control center. This motor control center feeds motors, right? So this pretty much covers the entire gamut of a system. And there's so many different rules and different industry standards and different specifications you have to follow, right? So you want to make sure if you have a panel, that it's designed properly, that it's fused. A lot of people install these panels in situations where they have a DC circuit, and the DC circuit, these molded case breakers can't be coordinated close enough. So what happens is if there's a miscoordination, it can take down an entire coker unit, right? So you want to use one of those DC panels for those situations. I know Eaton has a good panel as well. Here's major electrical equipment. Here, if you walk in one of these rooms, they're absolutely large, right? They're huge, right? And you want to make sure you've got the right maintenance space and that you've done all of your due diligence on your arc flash studies and whatnot. I've found equipment that's not rated for the short circuit current. I don't know if it happened over time or if somebody just didn't understand what short circuit was and installed a piece of equipment in the wrong place on the electrical system. So you want to make sure that when you do go through these systems that you walk through it, you understand it, and you help put these labels on these equipment. If you find a problem, don't say, hey, it's been working for 10 years. Stop it, mitigate the problem. If you have to, you can replace it, or you could put something in there to have it withstand that short circuit. I'm not sure off the top of my head. I think maybe a large inductor or something. Motors account for 70% of the energy consumed in refineries. Big deal right there, right? So you can look at these, but pretty much in a refinery, you want to make sure your motors are TEFC, totally enclosed, fan cooled, because almost every refinery has a minimum of a Class 1 Div 2 Group D classification, right? Probably T3 or so. And so what you want to do is you want to make sure that you buy TEFC motors. If you're dealing with hydrogen, I think there's a new standard that says you want to make sure that they're rated for class, Group B as well, right? And UL listed. On your protective relays, we talked a little bit about this. A lot of them have been replaced, but as you're doing your electrical studies, you want to go through the process and you want to identify these relays that should be replaced, and they'll actually help you become, they'll help you troubleshoot your system, right? So that's a big deal. So, and here's an older system, right, with these old Basler, looks like Basler relays, could be ABB or something, but that's a fairly old system, right? So you want to make sure you construct your TCCs correctly and you understand all these components. If you don't understand the components, get help, right? Grounding. Grounding is one of the most misunderstood items out there. People just don't understand it and they don't apply it. It needs to be installed properly. It needs to be separate from control systems, right? So if you have a power ground, you can have step potential problems, you can have all these problems. So here's an outdoor substation. It has a whole different set of rules than a local facility, or even your house or something. So you want to make sure that you understand your ground system, understand your grounding electrodes, and that you've done a ground study, right? So you can also have inadequate lighting or lightning protection. I've seen this, especially lately. We have had a lot of lightning strikes in Houston. And what will happen is if you don't have, and usually what I like doing is using that rolling sphere method, right? Where you take a large imaginary sphere and you roll it around your system and you make sure that this 25-foot radius or this 25-foot diameter ball is always hitting some grounded structure, right? If it isn't, you can actually have a problem and lightning can hit your critical piece of equipment. And here you see that Port Arthur had an issue where they experienced lightning that led to a power outage that also started a fire. So it just kind of goes downhill from here. So here what happened with a direct lightning hit or strike, we have overhead poles. Not a fan of them, but we have them. They're cheaper to install and everything. But when you have these overhead poles, they're going to get hit with lightning, right? So there is different types of lightning protection, fixed angle methods, rolling sphere method, and the proper grounding. No lightning system's going to work without proper grounding, right? So I'm not going to get too deep into this, but there is an introduction to power lightning protection, and you can go through it. This picture does a great job, right? So here you got this rod that sticks straight up, and it kind of gives you a cone, right, a little zone of protection. So if you did have lightning, smack, it'd hit that, and it would head straight down. You don't really see this too often, right? I know at my house I don't have it. Here they've covered a larger area, right, where they put two poles up, and they put a wire between them, a static wire, right? So you got to look at your air terminal height and your zone of protection. So here's an introduction to lighting protection. So if you can see here, they show you the angles and they show you these different things. But this is my preferred method right here. You take a rolling sphere, and you can do this in AutoCAD, and just roll it across your facility, right? And here they did 150 foot. That's a pretty big radius right there. And as long as you hit some metal grounded component, then you're protected, right? So, and you can do this, here it is, there's set distances that an air terminal can be insulated apart from each other on a roof or a peak within 2 foot of an edge of a roof, 20 to 25 foot maximum spacing along the ridge, right? So, it depends on what you're trying to protect and how you do it, but the rolling sphere method is probably one of the easiest and quickest ways to see your areas where you need to take a look at. Another area you want to look at is your recovery and restart. Once the power failure occurs, is the power going to come back? Utility is pretty reliable, especially in this area. Texas and the United States in general has some pretty good power. So usually it comes back pretty quick, right? So you have to have a recovery and restart method, right? You want to make sure you understand if a power failure occurs, what sequence or which ways are you going to start it up. I have seen so many people stay down for no reason other than the fact that they didn't understand why it shut down. And if nothing else, that is a good reason to go to a smart relay right there, to understand what caused the failure and what needs to happen to come back up and run. And you can do different SKM or ETAP model studies, and you can create different scenarios to understand these issues. Backup generators are a wonderful thing, right? Once you lose power, you can manually transfer, or you can do an automatic transfer, and you can wait until power comes back and until it's safe, right? And there's different generator manufacturers, but they're all about the same, right? And then you've got your uninterrupted power supply systems, right? An uninterrupted power supply system takes the AC, converts it to DC. The DC connects to a battery where you have a charger. That DC goes to an inverter, which steps it back to AC, and then you have a static switch around it. So you want to make sure you have those systems in critical areas where you really want to protect system, life-saving stuff, or even data automation centers and things of that nature. So here you got your input power, you've got all kinds of spikes, harmonics, undervoltage, interruptions, and you always get critical power out, right? Clean, critical power. So here's the 3 AC components, right? Here's your charger, like we said. We got the AC wave coming in, we've got DC coming out, and then in the middle right here is your battery connection right here. You've got this is your inverter, so it goes DC to AC, right? And then it comes back through, and you've got your a STS right here, which is your switchboard, I guess you will, with your static switch, right? So this is like a static switch. And then you've got a maintenance bypass as well. So, and it gives you an idea how that system works, right? If you have a failure, power flows through this way, right? If you have normal power flows through this way right to your load, right? To your critical load, and it also charges the battery. And if you want to, you can go to bypass source. This little manual bypass system right here, a lot of people leave it off. I highly recommend that you leave this in, because what will happen is this system will go bad and you can't replace it. So what you want to do is you can go back in there and you can say, hey, you know what, I'm going to put a UPS on my bypass source and I'm going to replace this entire system right here, because usually it's integral into one unit. So make sure you have some type of, even if a 2 breakers or 3 breaker system, where you can actually isolate that system and change it out, because it becomes very hard when it's integrated into your system. Another item is your batteries, the actual batteries themselves. There is a area classification issue that can result from these large lead acid batteries, and that is hydrogen evolution, right? You'll get hydrogen accumulation, and to the point where you exceed the lower explosive limit, or even 25% of the lower explosive limit, which is 1%. If you exceed 1% hydrogen in a room, you have now become a class 1 Div 2 group D or B area, right? It's a hydrogen area, so you need to mitigate that as well. One of the easiest ways to mitigate that is to have adequate ventilation, right? So here you get your battery charger. What we found during many site visits, pipe racks were severely overloaded. When we do a lot of laser scanning, I mean, even as a senior associate electrical engineer, project manager, I am not, I'll go out there with a laser scanner. And when I'm doing a job, if it's a known client that I do a lot of work with, if they are asking me to look at something early, like a proposal, sometimes I'll bring a laser scanner with me and I'll scan that unit, and then I know everything about that unit. I know all kinds of extra things, and I can see problems. I can see pipe racks bending. I can see them. You can physically see them in stress, right? So corrosion is causing pipes and pipe racks to fail. Overloading issues, area classification issues. There's so many issues out there. It's unbelievable, because people don't realize how to install this equipment, or they never were taught. They should have a practical. I guess we all learn that in the job. You got to learn that in the first couple of years. So new equipment added now creates an area classification issue. You might have a boiler installed with a fuel system or a fuel skid, and that fuel skid now encroaches on other equipment that has been general purpose. SIS, safety instrumented systems, or if you have a modified safety instrumented function, systems are not in place. Aging personnel, leaving behind young, untrained personnel. This happens all way too often, especially when you get people that that are managers that don't really understand everything about that facility, and these older engineers might not have been forthcoming on teaching people, maybe for job security issues or whatever. it becomes a real issue, right? And somebody can get into a bind. So it's our job as IEEE engineers and society members to help out other people. And if you have a problem and you're just unsure and you want to send me an email, I'll answer it. I will be happy to answer it. So you want to make sure that you have, one of the, we've seen this time and time again, right? Miscoordination of circuit breakers and fuses, undersized equipment, can't withstand the short circuit, or it can't withstand the continuous current. I've heard CEOs say, we don't have a problem with this facility. We don't have this problem in our facility, do we? And they had radial feeds, It's, they just assume that the process is completely redundant, that the electrical system is also redundant. And that's not always the actual case, right? So an electrical master plan addresses the reliability and safety of the existing electrical equipment. A report could be generated to mitigate long-term and short-term plans to improve the reliability and safety of the electrical equipment, supported by justification. Electrical cable and equipment needs to be reviewed to see if it support these structures in a good shape. So these are the things that would happen. And if you need help with what a master plan should look like, or if you work for a company and you're not sure, you've never done one, give us a call. We can give you some guidelines and stuff like that, or you can just use this document right here and kind of step through it. Another thing we did for the IEEE Overall Society, the CED, I think it was a CED training, continuing education development. We did understanding power concepts, and I have those slides. There's over 1,500 slides. 1,500 slides that Steve Sauer and myself put together and presented, and that was with a bunch of older engineers that were retiring, and they brought over all these old documents, and they said, you know what? I mean, literally, they brought over, a hand truck full of documents that we incorporated into that document. I need to somehow get it out to everybody via YouTube or something, or try to maybe record it and put it out there on YouTube. It's just a very, very long system of presentation. So, and to actually go through every item takes more than 15 hours, that's for sure. Develop an accurate system model. You want to make sure that you're doing this, that you use ETAP, SKM, Easy Power, some system like that. You want to understand your issues with your substation configuration. Are they radial or redundant? You want to identify your underrated equipment, your overloaded equipment. You want to understand what would happen if you had a voltage dip. What would happen if you had a single point of failure? What would be your short circuit capabilities? Short circuit capabilities change. Your short circuit utility data changes over time. If utility's doing something, if you've got a large facility coming in the neighborhood that you are currently working in, your short circuit current can change over time. So you want to be careful of that, right? So you want to put in long range plan theories, right? Can we consolidate equipment? Can we modernize equipment? Can we, can the equipment be maintainable, right? These are the things you want to put in. And like I said, I can't overemphasize, you want to sit in these process hazardous meetings. The electrical engineering needs to understand the processes, not only for the area classification studies, but also to commingle or to make sure that your electrical system is brought up to speed as the process changes. There's certain things that the process doesn't mind. They've already built in redundancies. They don't mind if they lose this, maybe they get a source of power from this unit and they get another source of power from this unit over here, and they have some redundancy in that unit where they have an A, B, C system. And as long as they have A, B and C can go away and they're fine, right? So you need to understand the whole deal. So the goal of the master plan is to determine the strengths and weaknesses of the existing system, determine the load growth potential, perform a reliability analysis, list recently completed projects, identify problems from the survey, list code-related issues, list grounding issues, list lighting issues, or lightning issues and lighting issues, list area classification issues, list maintenance department and operator complaints, confirm these complaints, and list your bad actors. A lot of times when I'm doing a master plan, I'll actually go to these different people, even people that have retired, and say, hey, if you could have changed anything, what would you change and why? Or another good one is, what keeps you up at night? What makes you the most nervous in this plant and why, right? They'll tell you. people will sit there and just tell you everything that they're nervous about, and it might be for a good reason, it might not be for a good reason, or it might be something that they just thought would be a problem. But you need to make sure you go through it. And you need to also find all the bad actors. And I'm not talking about bad people. I'm talking about equipment that fails on a regular basis, right? And there's usually about 5 different things that people say, gosh, every one of these breakers fails. And there's a reason for it. So you want to list them all out there. You want to look at system studies. Can transmission systems increase? Larger transmission transformers bring more capacity to distribution stations, limitations on the switchgear bus. Can system utilization be improved through power factor correction? I just ran into a client. We did a master plan for them, I think it was 2012, 2013. They had a poor power factor, but they weren't being penalized for that poor power factor. They are today. And they are getting a fine of he said, $500,000 per year because of a poor power factor. So that's an issue. Even in the report we said, that they had a poor power factor, but they weren't being penalized for it. If they ever were being penalized for it, we had some suggestions for them. So that was an interesting thing to come back full circle on us, right? So safety cannot be overemphasized. You need to make sure you put it in everything you do, right? Make sure your areas are identified and corrected, equipment replacement, setting adjustments, and other arc flash mitigation techniques. Make sure you have spare parts. Make sure that if it's a critical component and it's going to take 24 months to get, and it's that critical, and you don't have a redundant system, that you have a spare part in mind. One of the coolest things I've seen is one refinery has every one of their transformers size kind of the same. And what I mean is, if it's a certain size transformer, it has a center bus that's exactly the same on every one of the units. It has the same flange hole pattern. You can basically pull this transformer out and grab one from a different facility and put it in its place. And the reason they've done that is for this very reason. It works well. And I was just amazed when I saw it. I thought that was the greatest thing. You want to improve your maintainability, right? Ensure your A and B pumps are fed from different substation sources so that you're not shutting down. If process thinks that A is going to be available when B is not available, and you tie them to the same MCC, doesn't work, does it, right? You want to understand your turnaround schedules and make sure that your loads that are coming down on this unit are not going to affect another unit that's still expected to run. You want to improve your equipment maintenance through equipment design, and you want to have your draw-out breakers are easier to maintain than bolt-in breakers. So if you have an opportunity to have a draw-out breaker, you should usually have it, right? So consolidation, if you can consolidate, great. If you can go away from an older system and bring it into a building and have a main tie-tie main and improve your overall electrical reliability, that's the way to go, right? So, and then while you're doing your modernization of your older equipment, you want to get rid of your old electromechanical relays, go to the smart electronic or electrical relays so you can get some status and things of that nature, right? So, I guess this is a good one, right? Not everything is the same, right? So I said, in this case, I said PILC cables work real well with potheads. Well, they might work real well at one facility that's in a different environment. Maybe it's up north. And then down south, they have terrible problems with these PILC cables. Might be SF6 works better in colder climates versus oil-filled transformers or oil-filled switches. It might be that their maintenance crews love PILC or that they hate it and want it all out of the ground, right? So I've seen it both ways, right? So managers need to know the following. What are the lessons learned for petrochemical facility engineers and managers when dealing with the SIS systems or a lack of good SIS systems in place? That's probably, SIS systems are probably the most complicated thing I've ever seen. I just the hours and hours of time that they spend analyzing these systems and putting in place controls to make sure that there is an orderly shutdown or that there is a situation that is not created. It's phenomenal. It's just like one of the hardest things I've ever seen people do. But you want to have these discussions, and if you don't have these discussions and you never even heard the term, you need to start understanding it. You need to start looking at your facility and finding people that can help you go through these scenarios, right? So you want to go through your PHA and LOPA, right? Understand the power requirements, total connected load, running loads, utility required power factor, utility required harmonic distortion, right? Understand your voltage level available from the utility, your utility requirements for connection. So these are all the different areas that you want to understand. So you want to understand, your cable tray, your duct bank, your air insulated conductors. You don't want to combine different cables. Like if it's a 480 volt system or a 600 volt system or less, you don't want to combine that with a 5 kV system or a 15 kV system. There's certain things you just don't want to do, right? So you just want to basically understand your entire unit substation equipment, your power centers, your transformers, your switchgear, and your motor controls. You want to understand your classifications, right? Your classified areas, your blast zones. You want to understand if prefab buildings are more cost effective and a better solution than building on site, right? You want to understand your transformer loading and sizing, right? You don't, if you have a main tie main and you're running this A bus at a 75 or 80% of the total load and B bus is sitting there at 90%, well, then you don't have reliability, right? You don't have a backed up system. You want to understand your transformer grounding. You want to understand the high resistance grounding systems and your low resistance grounding systems. Sometimes these systems are not even connected, which is a disaster waiting to happen. You need to understand that. You need to have somebody walk through, check your grounds. I mean, they physically look at them to see if they're even connected, right? That's enough, right? So there's just so many different things involved here. It can be quite overwhelming, right? You want to understand your pumps, your compressors, your fans, your frequency, your variable frequency drives, all your different motors. You don't want to have a motor that's run on 480 volts that's greater than 250 horsepower. That's a nightmare, right? So you want to make sure of that. You want to make sure that you understand your radial, your primary selective or double-ended tie open, tie closed, or other variations. I know there's a lot there. I know there's a lot of information, but at the end of the day, you want to make sure that as an electrical engineer, that you're in the room with these different process engineers and chemical engineers, and that you understand exactly the way they're intending that these systems should be designed. And if they expect a redundant system, you are part of that redundant system, right, on the electrical power. So, and if you have an issue and you need to talk about it, certainly give one of us a call. There's a lot of different people out there that can help you out, and we're one of them as well. Thanks a lot.